Hello again, this is Professor Roman. Let's continue the lecture series Transition to Advanced Mathematics. It's time now that we spoke about functions in detail. This is one of the most important concepts in mathematics. But actually, just as there are two somewhat different definitions of binary relation, there are also two somewhat different definitions of a function, because ultimately a function is a binary relation. Here's the first definition. Let A and B be sets, and then as shown in this figure, a function consists of three things. A non-empty set A, called the domain of the function, which I'm going to write as DOM of F, and a non-empty set B called the codomain of the function, and finally a rule that assigns an element of B, the codomain, to each element of capital A, the domain. When this happens, we say that F is a function from A to B, and write it this way. If F is a function from A to itself, then we say F is a function on A. Functions are also sometimes called maps, and I use this term quite often. And then, as you probably know, we write B equals F of A to denote the fact that the function F assigns the element B in the codomain to the element A in the domain. Another way to say this is A is mapped to B by the function F. The element B in the codomain is called the image of A under the function F, and A is called the pre-image of B. The image of a function, not just the individual elements, but the entire function, the image of a function, which I'll denote by Im of F, and which is also called the range of the function, denoted by Ran of F, is the set of all elements of the codomain that are assigned to something from the domain. So we ship everything in the domain over by the function F to the codomain, collect all the results. That is the image or range of the function. And so it is a subset of the codomain. It might be a proper subset. But if the function has the property that its image is equal to its codomain, so in other words, everything on this side in B here is the target of something over here, then we say the function is surjective or is a surjection or is onto B. I should mention that the term range is sometimes used as a synonym for codomain rather than the way we're using it as a synonym for image. That's just the way it is. So when you read another book or listen to a lecture and you see or hear the word range of a function, you have to inquire, do you mean image or do you mean codomain? This definition that we just discussed is a tiny bit informal because there is no precise meaning, or we haven't given a precise meaning to the term rule. The alternate definition of a function, which is the one most often seen, I think, in books on set theory, doesn't suffer from this little informality. And it goes as follows. A function f is a binary relation, therefore a set of ordered pairs, with the property that no two distinct ordered pairs in f have the same first component. So that would look like this. If the ordered pair AB is in f and the ordered pair AC is in f, same first component, therefore must have the same second component. And it is, again, customary to write B equals f of A to denote the fact that this ordered pair belongs to f. So we can, to tie the two definitions together, an ordered pair AB in f simply means A is being mapped to B, or B is being assigned to A by the function. And we still have the image and pre-image definitions are exactly the same as before. One of the advantages to this definition, I suppose you might say, is that since a function is being defined explicitly as a binary relation, we already know what the domain and range of the function are. They're the same as what they would be as a binary relation. So the domain of f is the set of all first components of the ordered pairs in f, and that looks like this, where we're using this notation, the function notation, rather than the ordered pair notation. And the range of f is also already defined, so now we're going to have to say that the range of f is also called the image of f. And that looks like this. Okay. So the two definitions of function parallel the two definitions of binary relation, one as a subset of a Cartesian product, so you have the sets A and B in place, and the other as simply a set of ordered pairs. But the main difference between these two is the issue of codomain. There's no mention in the second definition here of the codomain. And therefore, strictly speaking, there's no concept of surjectivity. But we can fix that. If we want to insist upon the notions of codomain and surjectivity for functions defined by this second definition, what we can do is simply say that any set B that contains the image of the function, or the range, the same thing, is called a codomain, is called a codomain for f. So in this case, a function has infinitely many codomains. That's perhaps a little awkward, but it can be done. It works. Then we can say that f is surjective relative to the specific codomain, which is the image of f. And so for some choice of codomains, the function is surjective, and for one particular choice, and for other choices it's not surjective. We can also say f is onto B to mean that B is the image of f. So that's the alternative. I've seen that in various places, and it does work. For us, though, rather than agonize over which definition to use and what do we do about codomains, we'll just adopt the first definition. You need to know both definitions, but we will adopt the second definition because that'll serve our purposes just fine. So according then to our definition, we can write a function this way. The rule would be placed here, and A is the domain and B is the codomain of the function. So just as an example, this is a function on Q. Domain and codomain are both are equal to Q, and this is the rule. Now, this also, by the way, tacitly implies that x, the variable here, varies over the domain Q. So some authors, and I might also say 4x in Q here, but I didn't say it this time. It's not, strictly speaking, necessary with this tacit understanding. The variable here has got to range over the domain. It's the only thing that makes sense. Notice that this function, g, with domain Q and codomain R, but the same rule as f, is a different function because it has a different codomain. Under the second definition of function, these would be the same function with a different choice of codomain among the infinitely many codomains that exist. So I could replace this R by the complex numbers, and I'd have the same function, but I chose a different codomain. But again, we don't need to worry about that because we're adopting the first definition of function. We should also note that it is relatively common, in some contexts anyway, to omit the parentheses and write FA rather than F of A with parentheses. This tends to be more common in higher level books, but you will likely encounter it in upper division math classes. Of course, there are some times when you can't use the convention. For example, if you want to apply f to the sum, x plus y, you can't drop the parentheses or you'll get a different meaning. Just to be absolutely clear, so there's no confusion about this, because students often ask questions about this, this picture here shows a behavior that is not permitted for functions. This, whatever you want to call it, sends one element in the domain to two different elements in the codomain. Functions are not allowed to do that. This would be this would be an ordered pair language. The ordered pair AB1 and AB2 would both be in the function. And part of the second definition explicitly excludes that. Okay. Just for your own information, there are some contexts in advanced mathematics where you would be interested in maps that do this sort of thing. And they would be called multi-valued maps or multi-valued functions. This one, if that's all there was going on, is a two-valued function. But that's restricted to special contexts. In the study of complex analysis, for example, multi-valued functions occur regularly. So we will not have to worry about that. For us, the word function means exactly what it means from the definition, and it would be referred to as a single-valued function if there were also multi-valued functions floating around. On the other hand, this is perfectly acceptable behavior for a function, sending two different elements of the domain to the same element of the codomain, and we'll talk about that later. This is the property of being, well, in this case, not injective, not one-to-one. Some simple examples of functions. We'll let r plus be the set of non-negative real numbers. Then this is a function from r to r plus, f of x equals x squared. In ordered pair language, it would be this set of ordered pairs. If S is a finite set, and we consider the power set of S, we can define a function from the power set to the natural numbers. F sends the map A, the function, I'm sorry, F sends the set A to its size. Okay. And this is how it would look in order pair notation, the second definition of function. Another example with important applications, sigma is the set 0, 1. And sigma n, then sub n, is the set of all binary words over sigma of length n. We can define a function, h sub n, from the Cartesian product of sigma n with itself to n, to the natural numbers, by saying that if we have two words, w and u, in sigma n, then the function sends this ordered pair, wu, to the number of positions in the words in which they differ. So an example will make this clear. If n is 5, we're dealing with binary words of length 5. Here are two such binary words. To compute h5 of this ordered pair, we just check to see where the two words differ. They differ in the first position, and they differ in the last position. So in two positions they are different, so the value of the function is 2. These two words are identical. They differ in 0 positions, so we get 0. This function, h sub n, is called a Hamming distance function, named after the computer scientist Richard Hamming. The Hamming distance measures how close two binary words are to each other. This is a very important concept in the study of error-correcting codes. It's a branch of mathematics known as coding theory. So if you imagine, for instance, that you have, let's say, a space vehicle taking pictures of a planet, sending back information, sending back the pictures, it's going to come back in binary. So you're receiving binary words. Imagine you're storing information in memory of a computer or on a hard drive or a DVD being stored in binary. When you receive the information, there may have been errors, either in transmission or glitches in the storage. And the Hamming distance function will tell you how many errors took place. So it's a very important idea in coding theory. Here's another example with lots of applications. If A and B are non-empty sets, a function from A cross B to A is sometimes called a transition function. These are important in computer science, in particular in the study of what are called finite state machines. Transition functions are often denoted by the lowercase Greek letter delta. And the reason they're called transition functions can be seen from this simple example that I made up. Suppose A is the set happy, sad, and ecstatic. B is the set bad news, good news, great news. Then the transition function in this case will send sad, bad news to sad. So if you are sad and if you get bad news, you're still sad. If you're sad and you get good news, your state changes to happy. Okay? If you're sad and you get great news, you transition to the state of being ecstatic. So you see how the word transition and the word state comes into play here. This is a finite state machine. Let me just also mention that on rare occasions, you may encounter books where the author prefers to place the function after the element to which it applies. So you would see AF, or if parentheses are used, parentheses AF rather than FA or F of A. I just wanted you to know that. You may never encounter this, but you may, and so now you know that that sometimes happens. Okay. There are a handful of special types of functions, very simple functions that you should be very familiar with. Just as a reminder, this symbol is the Greek letter iota. It's a Greek I. And this symbol is the Greek letter chi. It looks like an X, but it's curved a little bit, and dropped below. It's lowered down a little bit. So it's definitely not an uppercase X. So when you write this symbol, try to be careful that it doesn't look like an uppercase X. So anyway, let A and B be sets. The identity function on A, so this has nothing to do with B, is defined by, I use the symbols iota sub A. It's a function on A, and it just takes every element to itself. Does nothing, then, basically. Some authors will write this as 1 sub A, but I prefer the Greek letter iota. If A is a subset of B, then the inclusion map, defined this way, it's the letter J is often used for inclusion. J sub A, mapping A to B, again sends every element of the domain to itself. So these two functions are very similar, they just have different codomains. Actually, if B is equal to A, then the identity function is in fact an inclusion map, but nobody thinks of it that way, I don't think. Again, if A is a subset of B, then the characteristic function of A is defined this way. Chi sub A, and chi is a very common letter to denote the characteristic function, maps B to the set 0, 1. And what it does is for the elements X that lie in A, they go to 1. The rest of the elements in B go to 0. So the characteristic function, which is sometimes called the indicator function, picks out the set A because an element is in A if and only if its function value is 1. Okay. These come up in various contexts, probability theory, for example. You may be familiar with the notion of a sequence from your studies in calculus. Sequences are generally defined as just in this form here. Let's see if I can, there we go. S naught, S1, S2, S3, dot, 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 where the elements or terms of the sequence, little s sub I, come from the underlying set, capital S. But this isn't a formal definition of the notion of sequence. And you know by now how important it is to have precise formal definitions that we can fall back on when the informal approach is not adequate. So here is the formal definition of a sequence. Let S be a non-empty set, and let M be any integer, and let us write Z sub M, this is the same Z we use to indicate the integers, Z sub M to be the set of all integers k greater than or equal to M. So M, M plus 1, M plus 2, and so on. Now, an infinite sequence, or simply a sequence in S starting at M, is a function. Little s mapping the domain Z sub M into S. And for any particular k greater than or equal to M, the kth term of the sequence is, of course, the element S applied to k. It's the function S applied to k, but that's generally written little s sub k. And so the image of the function little s is little s sub m plus 1, s sub m plus 2, and so on. It is what we informally think of as a sequence. It's the image of the function. The common starting values, the most common starting values for a sequence are m equals 0 and m equals 1, but there's absolutely no reason why you can't start a sequence anywhere you want. You could start it at negative 17. So you go negative 17, negative 16, negative 15, and so on. Or you could start it at positive 27, if that made sense. Now, the image of a sequence is generally thought of as being ordered. Sequences are thought of as being ordered. And that's why we write something like this. So this is the first element of the sequence, the second element, and so on. But strictly speaking, the image of a function doesn't have any order associated with it. So the order we place on sequences is the order that comes from the domain. So we say that s sub k precedes s sub j in the sequence if and only if k is less than j. So we transfer the order from z sub m to the image of the function little s, and we get an ordered image, and that is what is informally thought of as a sequence. Note also that the image of an infinite sequence can be finite. For example, here is an infinite sequence because we are mapping the natural numbers, so this sequence starts at 0, and the function takes every natural number to 1. So it is what we would refer to as a constant sequence, 1, 1, 1, ... The image then of this sequence, this function, is just a set containing 1, which is certainly finite. But that doesn't make the sequence finite. This is an infinite sequence because the domain is infinite. Got a couple things to fix here. Now let's take a look at composition of functions. Suppose we have a function f from a to b and another function g from b prime to c, where b prime is a subset of b. And here's the picture. F maps a to b. This is the codomain of f, the set B. Inside the codomain sits B prime. It could be all of B, but it doesn't have to be. And G is a function on B prime going into C. Now, if the image of F is contained in B prime is the domain of G, so image of F contained in B prime equals domain of G, then we can apply the second function G to the elements in the image of F, because they're contained in the domain of G. And so we can define a function from A to C in words by first apply F and then apply G to the result. And that's guaranteed to be a legal operation because the image of F is contained in the domain of G. So to illustrate, I guess I should say, so the resulting function is written this way, G circle F. So F is being applied first, and then G. Sometimes it's just written GF. and it's called the composition or composite of G and F. And you have to be careful about order here. G circle F is not the same as F circle G. In fact, oftentimes one will exist and the other won't even make sense. But there are times, for example, if A, B, B prime, and C are all the same set, then you can take the composition in either order. But that doesn't mean that they're the same. They're generally different. Here's an example. S is a finite set, and let X be an element that is not in the set S. So I guess I probably should have said let X be some set that is not in S, but element is fine. Define a function F that takes the power set of S to the power set of this union. In other words, S with X tossed in. And the rule is that a subset of S is sent, say call it T, is sent to T union the set containing X. So this is the toss in X function. Okay. I said here include X. That sounds a little bit more professional. So the function F is include X. G is another function on the power set of S union set containing X to the natural numbers, and it's the size function, the size of a set. So if I compose these two, G circle F, it's going to map the power set of S to the natural numbers. Okay? And if you apply this composition to a subset T of S, first you apply F, then you apply G. When you apply F, you get T union the set containing X. G is the size function, so it's the size of T union set containing X. And the size of this is 1 greater than the size of T. So the composition sends a set T, a subset of ST, to 1 bigger than its size. If F is a function from A to B, then it's often quite useful to either restrict F or extend F. And here's the formal definition of these two processes. So we have a function F from A to B, and let X be a set. I think it probably should be a non-empty set. Okay. If X is contained in the domain A, then we can restrict the domain of F to X. So we haven't changed the rule, we've just restricted it to the elements of X. And that gives us a function which is often denoted F vertical bar subscript X, mapping now the new domain X to B, which was the original codomain. And this function is called the restriction of F to X. The process doesn't change the codomain, but it may affect the image. And generally, if you restrict the domain, you're likely to restrict the image. Doesn't have to be true, but oftentimes it is. Going in the other direction, if X is a superset of the domain of F, then an extension of F is a function G from the bigger domain, now the bigger set X, to some other set that agrees with F on the smaller domain A. So G of A equals F of A for all A and X. Examples, we can restrict this function. This is the function on Q that squares everything. We can restrict it to the integers. So So that means we restrict the domain, we write the new function in with this notation. This is the same codomain, and it's the same rule, but only applied to integers. We can extend f to a function on the real numbers, and the rule is the same in this case. So I'm extending this function to this one. Another extension of f might look like this. This is the function h mapping r, again, real numbers to themselves. H of r is equal to r squared if r is in Q. That has to be because an extension has to do the same thing that f does on the domain of f, which is Q. But on the rest of R, in other words, the irrational numbers, we can do whatever we want as long as it defines a function. And so h I've chosen here to send every non-rational number, every irrational number to 0. And so that's an extension of f. These two processes, restriction and extension, are very common in mathematics, and you will encounter them many times in your future studies. Let's talk now about some important properties of functions. We've already discussed surjectivity, but let's take a little bit closer look. A function f from a to b is surjective or surjection if its codomain is equal to its image or range. And this is what it looks like. And then we can say that f maps a onto b rather than into b. It always maps into b, but the surjective functions map a onto b. So the words into and onto are actually mathematical terms. Loosely speaking, a surjective function doesn't have any unused elements in its codomain. Its codomain is as small as possible. It's equal to the image of the function. Example, if I'll use r sub greater than or equal to 0 to denote the set of non-negative real numbers. So this function, f, on the real numbers, f of x equals x squared, fails to be surjective. It's not surjective because its image is the set of non-negative real numbers, but its codomain is the set of all real numbers, so that's a proper subset of the codomain. But if we change the codomain, make no mistake, we get a different function. Let's call it g. Now it maps r to the non-negative reals. Same rule. This is surjective. So it's important to be clear that surjectivity is solely, strictly a property of the codomain of a function. And it's often convenient to redefine a function when necessary. To get a new function, we redefine it by reducing the codomain to the image, and that makes the function surjective. And of course, it's very similar to the original function. We've just thrown away elements in the codomain that weren't used in the first place, but still, by definition, it is a different function. The composition of surjective functions is surjective, and the proof is here. We have a function f from a to b and g from b to c that are surjections. To show the composition as a surjection, we have to show that every element in C has a pre-image in A under the composition. So if we take a little c and capital C, that does have a pre-image in B under G, because G is surjective. So there's a little b in B for which G of B is mapped to C. But similarly, B has a pre-image in A under F. So there's a little a and capital A for which f of A is B. And we put those together. C equals G of B equals G of F of A. And so this composition, G circle F, has a so C has a pre-image under this composition, and that pre-image is A. And so the composition is surjective. We mentioned earlier, and there's a figure 11.3 you can look up. It's possible for a function f from A to B to send two different elements in the domain A to the same element in the codomain B. Functions that don't do that are called injective functions or injections or one-to-one functions. This is what it looks like in symbols. If A1 and A2 are different elements of the domain, then f of A1 and f of A2 are different elements of the codomain. Another way to say that is by the contrapositive, which is often more useful, but they're equivalent, of course. F of A1 equals f of A2 implies A1 equals A2. Same image, same pre-image. Example, function on the natural numbers f of n equals n squared is injective because m squared equals n squared implies m equals n for natural numbers. If we upgrade the domain and codomain to the integers, g mapping z to itself, and same rule, g of z is z squared, this is not injective. Because now we have negative numbers, and, for example, -1 is different from 1, and yet when we apply the function, when we square, we get the same thing. Another example involving the sine function, I'll let you look at that. The restriction of an injective function is injective. Excuse me. That's not true for surjective functions. When you restrict a surjective function, you're cutting down on the domain. That may very well cut down on the image. And so if the function was originally surjective, it's not necessarily surjective anymore. Also, the composition of injective functions is injective, and that's true about surjective functions as well, as we just saw. So here's the theorem for injective functions, and I'm leaving that for you to prove as good practice. Here's a result that is of great use at some time. Doesn't get the attention it should. It should be mentioned explicitly somewhere, and so I'm doing that now. F is a function from A to B. G is a function from B to A. So these are functions that you could say informally point in opposite directions. If their composition, G circle F, is the identity map on A, then we can say something very important. So here's the same setup. F is injective and G must be surjective. This composition implies F must be injective and G must be surjective. As to the proof, the injectivity of F, we just look at the definition. If F sends A1 and A2 to the same place, we can apply G to both sides. The composition is the identity, and so A1 equals A2. And that means that F is injective. As to the surjectivity of G, we have this equation, because G circle F is the identity on A, And so f of A is a pre-image of A under G. Therefore, and since little a was arbitrary, every element in capital A has a pre-image under G. Okay. And so G is surjective. If you're worried about remembering this, when you see this, you should think, well, something's going on. One of these is injective and the other is surjective. I can't remember which. Think about it this way. If F were to send two elements in its domain to the same element, G is never going to undo that. Once that's done, as far as G is concerned, all it sees is the image. So it sees just the one element. So you're never going to recover, and so which means you're never going to get the identity, because the identity doesn't send two elements to the same element. So F is the one that must be injective, and then by default G is surjective. So hopefully that'll help you remember. A function that's both injective and surjective is said to be bijective or a bijection. And another term for that is one-to-one correspondence, but that's not, that term is generally used in certain contexts only. In set theory it's used, in combinatorics it's used. I'm sure there are other places where it's commonly used, but in places like analysis, in calculus, for example, one doesn't generally refer to a bijective function as a one-to-one correspondence. They just call it bijective. Okay. And I'm going to leave for you to prove that the composition of bijective functions is bijective. It is precisely the bijective functions that can be reversed. And what I mean by that is the following. Here's a picture. F is a function from A to B, and if it's bijective, then every element in capital B has the form f of little a for some A in capital A. That's the bijectivity. Actually, that's the surjectivity. The injectivity tells us that the pre-image A is unique. So every element in B has a unique pre-image in A under F. So we can define a function going the other way, the pre-image function. That's not the technical term for it. The technical term is the inverse function, denoted this way. And so it maps B to A, and it sends little b to its unique pre-image, little a. Since B is f of A, it could also be written this way. The composition, F inverse composed with F, is in fact the identity on A. It sends little a to itself. Okay? So you can think of it as the pre-image function, but when you speak out loud, you should call it the inverse function. And it's critically important to remember that a function is invertible, has an inverse, if and only if it's bijective. You need the surjectivity to guarantee a preimage, and you need the injectivity to guarantee that the preimage is unique, so you know how to go backwards. If there were two preimages for one image, you wouldn't know which one to choose. You wouldn't have a well-defined function F inverse. Now, of course, we can do something we discussed earlier. If you have a function f from A to B that's injective but not surjective, we can change the codomain to get a new function, but of course very closely related to the original one, that is now surjective. We drop the codomain down to the image. That's now bijective, and so it is invertible. One way to characterize inverse functions is by composition. A function f from a to b is invertible with inverse g if and only if the composition in both directions, g circle f and f circle g, are identity maps. They're different identity maps. One is the identity on A, because that's the domain of f. The other is the identity on B, because that's the domain of G. Okay. As to the proof, let's say first that f is invertible and G is f inverse, the preimage function. We've already seen then f inverse of f of a is a, which means G of f of a is a. So G circle f is the identity on A. The other way around, f of G of B, little b is in capital B, is f of f inverse of B. And f inverse of B, as we know, is the unique preimage of B under f. So when we apply f to it, we get B. So f circle G is the identity on B. As to the converse, we get to suppose that both of these are true, and we have to show that G is in fact we have to show that f is invertible and G is the inverse of f. Well, the theorem we just got through doing that I said was very useful at times is useful here. This composition tells us that f is invertible and G is, that f is injective and G is surjective. Okay. This one tells us the opposite. G is injective and f is surjective. So they're both bijective. That was easy. We used this theorem twice. So it remains for us to show that every little b in B has a unique preimage, and that image is G of B, and that will tell us that G is f inverse. It's the preimage function. So first of all, f of G of B is the identity on B of B, so it's little b. So that tells us at least that G of B is a preimage of B under F. But if A is also a preimage of B under F, so F of A is B, then if we apply G to both sides of this and use what we're allowed to assume here, we get A equals the identity applied to A equals G of F of A, and that's equal to G of B. And so G of B is in fact the only preimage of B. In other words, it's the unique preimage of B. And that's what we wanted to show. So G is in fact F inverse. I want to emphasize that if we have a function f from a to b and a function g from b to a, this condition by itself, it's one of the two conditions that are here, just one of them, tells us, as we've seen, that f is injective and g is surjective. It's not enough to tell us that g is the inverse of f. You need both of the conditions. You need the composition in both directions to be identity maps in order to conclude that G is F inverse. And incidentally, then F will be G inverse because there's a symmetry here. But it's worth also mentioning that some authors actually use these two conditions as the definition of F inverse. G is the inverse of F by definition if these two compositions are equal to identity maps. That's fine, nothing wrong with that, but then you do need to show that G is unique. Okay? If you expect the inverse to be unique, which it is. The way we defined the inverse of F is as the preimage function, and that's unique because the bijectivity of F tells us that every element in the codomain has a unique preimage. So the preimage function is really the unique preimage function, and so it's unique. There's only one. So we got the uniqueness of inverses automatically by our definition of inverse. If you use this definition as inverse, you do need to show that there's only one G that fits both of these. Okay, we've got a couple more things to discuss concerning functions. And the first one concerns what are called induced functions. So if we have a function f from a to b, this induces two other functions. One is called the induced direct function. And the way that works is this. If x is a subset of the domain A, then we can just restrict, we can apply f to the elements of the subset x and collect the resulting images into a set which would be a subset of B, and that would denote that by f of the set x and call it the image of x under f. So in symbols, f of capital X is the set of all f of little x's as little x ranges over capital X. Okay. And this does define a new function because now it maps the power set of A, the power set of the original domain, to the power set of the codomain. Okay. But it is customary to use the same symbol f for this new function, but it is a new function, it is a different function. On the other hand, and this is called the induced direct function, but on the other hand, this is such a common thing to do that mathematicians generally just think of this as the original function. And so they say, well, a function maps A to B, but it also maps subsets of A to subsets of B, and they don't bother with the term induced direct function unless there's some need to use it. So this becomes rather informal. Okay. The induced inverse function, however, is a little more formal. We have a function from A to B, and if we take a subset of the codomain, we can collect all of the elements of the domain that are mapped by f into that subset of the codomain. Or put another way, all pre-images of the elements in the subset Y. Now, some of those elements in Y may not have a pre-image. That's fine. We don't have anything to collect. Some may have multiple pre-images if the function's not injective. That's fine. We collect them all. So it looks like this. F inverse, that's the notation for this, of the subset Y of the codomain is the set of all elements in the domain that are mapped into Y. This is called the induced inverse function, and that is the term that's used. And but the notation is still F inverse. But now it maps the power set of B to the power set of A. So we're duplicating the notation here as is customary. Okay. The important thing to note here is that Well, it's only the bijective functions that have real inverses, ordinary inverses. Every function has an induced inverse function. And that's one of the reasons, one of the major advantages of using induced inverse functions. Okay. So just to summarize, here are the two definitions I just gave you. One interesting thing about these induced functions is that the induced inverse function is actually more well-behaved than the induced direct function, at least when it comes to preserving set operations. So here's a theorem whose proof I'm leaving for you. F maps A to B. Then if we have a family of subsets in the domain, and we apply the induced direct function, f, to the union, that is the union of f of the individual subsets. But the intersection, f does not preserve the intersection. F of the intersection of the family is contained in the intersection of f of a. So the induced direct function behaves nicely with respect to unions, but not so nicely with respect to intersections. Okay? This can be a strict inclusion. But the induced inverse function behaves nicely with respect to both unions and intersections. Finally, to conclude our discussion of functions, we need to talk briefly about increasing and decreasing functions, which you may very well be familiar with from calculus. But I just want to go over the terminology because there are some inconsistencies in the literature. But we can also generalize this to functions between partially ordered sets. So P is partially ordered by this symbol. So is Q. I've used the same symbol here for the order, the partial order, and that's commonly done. But it does not mean they're the same partial order. The partial order on P isn't generally going to be entirely different than the partial order on Q. Okay, but sometimes, and this happens, a symbol is used in two different contexts. And you have to get used to that. So we can define what it means for functions to be increasing and decreasing, functions from P to Q. This is the picture you probably have seen in a calculus class, but here's the definition. So we have our two posets, and we have a function from P to Q. F is strictly increasing if a less than b implies f of a less than f of b. And that would look something like this for the case of functions on the real line. F is non-decreasing if a less than b implies f of a less than or equal to b. So we have this picture where there's a flat here. F is strictly decreasing if a less than b implies f of b less than f of a, and non-increasing if a less than b implies f of b less than or equal to a. These are the terms I use in this course. I use it all the time in all my courses because there's no ambiguity. But there is variation in the way these terms are used. Some authors will use the unmodified term increasing to mean strictly increasing. Some will use it to mean non-decreasing. So you have to be careful when you read other books, when you see a term, the terms increasing or decreasing, to check and see what that means exactly.